Hey everybody, this video is on section 4.2, the mean or expected value, and a little bit on standard deviation. So the expected value is a term that shows up in terms of probabilities and an outcome, and it's what's going to be referred to as the long-term average or mean. So it's going to be what we expect to happen in the long run. So just for example, long run means what happens over a lot of trials. So what's the probability if flipping a coin? What's the probability the result is heads? We know it's 50-50, but if you do 10 flips, as we saw in our earlier demo, you might get 4 heads, 6 tails. But if you do this a million times, such as this story is, or sorry, no, 24,000 times, this person ended up with right around 12,000 heads, 12,012. And this is just supposed to show the law of large numbers. And hopefully you've heard about that before, and we've talked about it a little bit. So we're going to use the law of large numbers to help us find the long-term results of statistical experiments. So we're going to calculate what's known as the average outcome, the long-term average. This is mainly called the mean or expected value. And we use the Greek letter mu for this, lowercase mu right there. So it's going to be telling us, after conducting many trials, what we would expect in the long run. And to find this, we simply take this equation. And this equation looks complicated, but it's really not. So the mu stands for the average or the expected value. This capital sigma stands for the sum. It's going to be the sum of all of our outcomes multiplied by our probabilities. So we just take each outcome, each probability, multiply them together, and then add all those up. Let's do a few examples. Here we have a soccer team playing 0, 1, 2 days a week. Probability they play 0 days is 20%, 1 day is 50%, and 2 days is 30%. Find the long-term average or expected value, the mu, of how many days of soccer they play on an average week. So to find the expected number, we multiply each value by the probability. So here's our table that we looked at last time, our probability distribution table with our probabilities and our outcomes. So 0 days, 1 day, 2 day. And what we're going to do is multiply these together. So 0 times 0.2, 1 times 0.5, and 2 times 0.3. And this will give us our expected values over here that we're going to add up. So the first one is 0 because that's 0 days a week. And so that adds no days a week of extra soccer. This 1 day a week soccer that happens half the time gives us an expected value of 0.5, which kind of makes sense because half the days we play 1 game of soccer, or half the weeks we play 1 day of soccer. And so half that would add half because it's only happening half of the time and it only counts for 1. But the 2 days a week, that happens 30% of the time. That takes us to 0.6. Then we add all these together. So 0 plus 0.5 plus 0.6, adding that we get 1.1. So the expected number of soccer to be played per week is 1.1 days on average per week. Some days there's 0, some days there's 1, some days there's 2. The most common result is 1 day of soccer, but on average, it would be 1.1. So suppose we're like trying to calculate, I don't know, like maybe like a pair of soccer shoes runs out after 100 games. Just completely made that up. So then you could figure out after how many weeks you would need to get a new pair of shoes, because we don't play, even though 1 is the most common amount of soccer played per week, we actually average 1.1 games of soccer per week. Let's do another one. A little more complicated. Playing a game of chance with 4 cards drawn from a standard deck of 52 cards. To win this game, you have to guess the suit of each card before it's drawn. So there's a draw, 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 draw. 4 different draws. And you have to get all 4 of those right. The cards are replaced in the deck after each draw, just to make it a little simple. It's $1 to play. And if you win, you get $256. What's your expected profit or loss of playing the game? So to do this, we need to calculate our probabilities. And we calculate our profit and loss. So if we lose the game, we lose the buy-in, the dollar. But if we win the game, they say we get our money back, so the dollar back, plus $256. So that's going to be a net profit, a net win of $256. Now let's calculate our probabilities. To get this right, we need to pull out, we need to say diamond and then pull the diamond. It's heart and get a heart. And in a deck of cards, there are 4 different suits. And if we put it back in, the probabilities won't change. These are independent events. So what we will do is find the probability of each event occurring. So we have 4 suits. So the chance we get that suit right on the first draw is 1/4. We put it back, shuffle, pick the suit again, pick a suit. Another 1/4 chance. So we have 1/4, 1/4, 1/4, 1/4. Very hard to have happen. We need to be successful on all 4 of those. So it's 1/4 to the 4th power. It's 1 over 256. So about 0.0039 chance of happening. Or if we turn that into a percent, 0.39%. All right, so now we have our probabilities. Here's our nice table. Here's our chance for success. And then what we did was we take, if this is our chance for success, the other outcomes are losing. So here's the chance for a loss. And what we're going to do is multiply these together. Notice these add up to 1. So we take the outcome multiplied by the probability for each event. And here we get our calculations. So success plus the loss, we get this and this. We end up with 0.0023, and our units were in dollars. So that would be 23 cents. So on average, we are making 23 cents every time we play this game, which, let's see. Yeah. Which would give us just a small little profit. Most times you would lose the dollar, right? But sometimes you would get that 256 plus your bet back. And so, if you play this game 100 times, that probably wouldn't be a large enough sample, but maybe you played this game 1,000,000 times if it happened on a computer or something. Then you would show a 23 cent on average profit. So that's expected value.